You probably came from the Artifacts video that came out recently. And you are here because you're interested in what I've done, which is cool. So, then, what is an analemma? How is it caused? And why do you need to know about it? So, an analemma is a shape that is created by the sun. It is the path that is drawn by the sun if you were to take a picture at the same time every day. My program only shows the sun, it only shows the analemma from the sun's perspective. I'll get into what that means later. Which means that it is not accurate to what you will see on Wikipedia. I'm not going to show that up, you can just go search it. So then, what causes an analemma? There are three major things that cause an analemma, but we're only going to talk about two of them because the third thing varies so much and is, as far as I know, can only be done through simulation because it is based on basically everything else. It is caused by weather, it is caused by the planetary motion of many other things, all of which you would have to factor into this, and I don't have time for that, and my program is running slow as it is, so let's not worry about that. So then, what are the other two things? First one is axial tilt, the tilt of the planet relative to its orbit around the sun. Why is this important? Well, the analemma goes up. As you can see, the sun changes position vertically, north and south. This is caused by the axial tilt. The axial tilt doesn't change at all while it's going around the sun. And because it doesn't change at all while it's going around the sun, it stays at this constant sort of thing. At some points it's tilted towards the sun, and other times it's not tilted towards the sun at all. You can see what it looks like from the sun's perspective down here on my program, on my calculator. And because of this axial tilt movement, when it's tilted toward the sun, the north is tilted towards the sun or away from the sun, that means that the sun is physically looking from Earth more southward or more northward. That's what axial tilt does, right? That's the explanation that you'll hear everywhere. I'll go into more detail about it just a little bit, but before I get into the next thing, let's just say that this detail is slightly wrong. It's true, but it leaves out some very important details that I had no idea about when first making this program. So the second thing is orbital eccentricity, basically how circular your orbit around the sun is. That is shown up here. You can type in the value here, and that will change very little, actually. I said that there are three major things that cause axial tilt. Well, sorry, not axial tilt, sorry, analemmas. But I'm going in order of severity. Axial tilt is the biggest. Eccentricity hardly does anything at all. You may say, hey, you just explained the vertical motion. Then doesn't the eccentricity cause the horizontal motion? And it does, to an extent. It in reality hardly does anything at all. The third thing, like I said, I'm not going to go too much into it, is actually called wobble. That is the official term, I think. As far as I can tell, the term is wobble. You can search it up whenever you want. And it only changes the analemma every, I don't know, 26,000 years. So I don't really think it matters all that much. It can, assuming that you're doing a very large thing, but this calculator doesn't do it, as for reasons I explained earlier. So, then, what does eccentricity do? So, low eccentricity actually hardly does anything, but basically, the best way to explain it is that the Earth rotates at a constant speed. But because there are points along the orbit where you're closer to the sun and farther away from the sun, and as you may know if you've taken an astronomy class, that changes your speed along the orbit. Basically, the closer you are to the sun, the faster you're moving around the sun. The farther away you are from the sun, the slower you're moving. And because the orbit is not perfectly circular, that means that the planet changes speed along its orbit. So what happens when you change your speed along the orbit, but have a constant rotation? Your length of day actually changes. The day of the Earth is not determined by how long it takes for the Earth to rotate 360 degrees. It's how long it takes for it to rotate and see the sun again. Or at least that's the best way to explain day if you don't have a clock. Because our version of day is called solar mean time, which is the average of all days across a year. But anyway, the length of a day changes. And no, not in terms of there are short days, long nights in winter, and long days, short nights in summer. This is a completely different phenomenon, where the whole length of the day changes because you are moving slower in the orbit at some points and you move faster at others. But because the rotational speed is the same, when you're over here hardly moving at all, the Earth basically has to do a 360 turn. But if you're over here and going really fast, then it has to make a more than 360 degree turn, which means that the sun changes position east and west. Because rotation is predominantly an east and west thing. It moves the Earth east to west. No, sorry. The Earth rotates west to east, which causes the sun to move east to west. Bit confusing, I know, but stick with me. But like I said earlier, the Earth moving faster means that it has to rotate more than 360 degrees, which means that a day there is longer. Yes, it takes longer for the Earth to rotate around for the sun to be in the sky in the same place again. So, yeah, like we said earlier, that means that the east-west motion of the sun is what causes this figure 8 pattern. Wrong. Earth's eccentricity is quite small, and because of this, it hardly does anything to the analemma at all. In fact, the only thing that I'd say that actually happens when you change eccentricity is the difference in the length between equinoxes. Sounds a bit strange. Actually, no, that's wrong. It changes the length of the seasons. That's a better way of saying it. It changes the length of the seasons individually. Because, you might not know this, the 4 seasons are not exactly a quarter of the year long. If that were the case, then the distance between the 2 equinoxes would be the same. And what I mean by that is that the distance from I don't know the name of equinoxes, so I'm going to make up things as I go. The northern fall equinox to the northern spring equinox is a different amount of time than the other way around, going from spring to fall. Those 2 times are completely different. They're similar, but only because the eccentricity is small. But they are different. They are different, I believe, by a couple days. And that will be important for your world, assuming that they have enough technology to see this. Or assuming that the eccentricity is high enough that it will be visible. So then, what does cause this east and west movement? Well, I already mentioned it earlier, axial tilt. But why? And I'm going to pause here for a second. This thing was so annoying to find on the internet. It doesn't exist. It just doesn't. I can't find it anywhere. There's no place that explains how the east-west motion of the sun in an analemma is caused by axial tilt. There are a couple places that there are people asking about it, and others are like, oh yeah, that's true, or oh, but you're missing this one detail, which is that the Earth's axial tilt causes east-west motion. But no one, and I mean no one, explains why. At all. So I had to come up with my explanation myself. So we are now going into uncharted territory that I have no idea if this is correct or not, but it seems logical to me. As mentioned earlier, the axial tilt stays the same as it goes around the sun. But because of that, and from the sun's view, the axial tilt shifts. If we move this slider, you can see that the axial tilt changes like this. And this right here is a diagram directly from the sun's point of view. This is what the Earth's axial tilt actually looks like from the sun. But here's the thing. The Earth's axial tilt is also tilted toward or away from the sun. Slightly. This was a bad example because this is basically exactly on an equinox. But if I go like there, this is tilted, let's see, it's springtime, which means that we're going into summer. We are slightly tilted towards the sun in the northern hemisphere, which means that this isn't exactly flat against it. It is slightly tilted towards the sun as well, like that, basically. And because of that, the sun isn't moving across the equator. It's moving slightly above the equator. But the sun and where it's positioned in the sky, solar noon as it's called, when the sun is directly above a certain location, is a perfectly vertical line up and down. And we're slightly above the equator. But that means that the point at which the sun is not on the equator, nor is it on this axis of the axial tilt, which means that it must be to the side of it. And because it's to the side of it, it causes east to west motion. East and west motion. I need to stop saying east to west because it changes its direction all the time. Anyway, that's what causes it. It took me like 2 weeks to figure that out. By the way, this project took like a little bit over a month, though it took time between when I was personally fully done with the project and when I showed it to Artifactsian. And that in that time, I decided to make small adjustments, and those small adjustments are inside of the program. But they aren't major. Or actually, no, I should say that they are major, but only for small things, like the eccentricity. Like, it only affected it if the eccentricity was super high, which you're not going to do for habitable planets. And as you'll see later, this is really useful for habitable planets, or planets that are inhabited, I should say, because some uninhabitable planets can be, geologically changed to be habitable. So yeah, Analemma is basically a thing that is only used where people live. It's not used for anything else, as far as I know. Speaking of which, though, now that this is explained, why do you need to know it? Well, why would you want to know? Well, earlier I was trying to figure things out, and I said that it was spring. Well, that's determined by when equinoxes and solstices happen. The equinox is exactly when the sun is at the equator, not at this cross point. This cross point is not at the equator. You can see that by changing the eccentricity. Make it high, and this point will go up. And actually, that's the reason why the equinoxes have different lengths depending on which equinox you're going between. It's because they don't meet at the center point, I think. I actually haven't checked that, but also I don't want to check it because I think it'd be annoying. You can check it if you want, assuming that you're math savvy. But mathematically savvy, I should say, because the other way I said it could probably sound like something different. Anyway, the spring spring and they're determined by the equinoxes, which are different lengths of each other because it's when the sun reaches the equator, not this midpoint. And okay, so when do you know when these equinoxes and solstices are? Well, that's determined by you. This is where the solstice happens, the north solstice. I know that there's an official name for it, but this was made before I learned that, so that's why it doesn't show that. And then this determines, well, actually, this determines when the Earth is closest to the planet, which on this diagram at the top left will always be to the right. Always. And the farthest will always be to the left. Now, something interesting is that if you have a solstice or an equinox exactly at the point of I forget the official name. Perihelion is for the Earth around the sun, but there is an official name for star systems, and I forget what it's called. Anyway, if it's exactly at that point, then it's opposite. For north solstice, it's the southern solstice. If for north fall equinox, it's the north spring equinox. Those will be the same length apart. They will be the same amount of time between the two. That's because the amount of time that it takes to traverse half the orbit from Peri is the same to travel half the orbit to Peri. It is not true if you're traveling half the orbit along other axes, but it is true for Peri. So, okay, time to actually get into this. What is this good for? Like I said, it can tell you when spring, summer, winter, and fall are. Spring, summer, fall, and winter. But it can also tell you the length of a day in a region depending on the year. Let's say that your colony lives, I don't know, and I'm just going to pretend that this is a fictional world. Let's say that they live on this continent here, whatever this continent is named in your world. And they live like right there. You can tell that at this time it's night. Now, what time is this? This is day 0, year 0. You can obviously add any offset to this that you want, but I suggest that you don't add an offset. You don't start here and add your offset, because this lines up perfectly to when the year happens. This lines up perfectly where the beginning of the day is the beginning of the year. And that is not true for real life. That, like, you will never find something that does that. So I suggest adding like a couple years to the day counter. So you come down here, you look at this, right? And you take this and you multiply it by like 5 or something. You can multiply it by any number you want, but then you input that as your current day. As you can see, it is the very beginning of a year. But the day, as shown by this white line, because this is where the prime meridian is it's not daytime. It's not at the edge of the map like it was before. It's now here. So this is a much more accurate version. So if you're living here, you can tell the exact length of the day at that point. You can see that if this continues very, very slowly, right? you can see that it becomes day. Oh, whoops. Let's say that you live at this point right there. It is a day right now. Okay? It is turning day. Then if you let this run for a little bit, and then stop it, at the point that it turns night at that same location. Went a little too far. I think there. Now you have these two numbers. -1 from the other. Then multiply it by the length of your day. Now this is the mean time that you want to multiply it by. The average length of the day across the whole year. For Earth, it's 24 hours. For your world, it will be whatever you put in Artifaxian's spreadsheet. And you will see that the length of day at that location is exactly 12 hours and 12 hours. Do a little bit of math. You subtract the two numbers, right? Then you multiply it by the length of your day in hours, and you'll get exactly how many hours it is. Then you take, and this will not be a whole number, okay? So this will not be a whole number. You want to take the integer portion of it, which is 12, and then you want to take its remainder, what's left over after the integer portion, and you want to multiply that by 60, which is the number of minutes in an hour, which of course we define as 60. But if you have your own unit in your own world, then you're going to want to use that unit, assuming that that's what you're using in your story or whatever. So you can see that this bot in Australia is in 5 years. By the way, I made this calendar start at exactly the beginning of 2024. But do know that the exact time of day is wrong. Like I said, this is supposed to be a general thing for people to use for their worlds. This is not a scientific thing. Well, it is scientific, but it's not like Earth accurate. It's not entirely accurate to Earth. Anyway, in 5 years from now, the day on Australia at that point will be basically 12 hours and 38 minutes long. About. And so using this, you can find the length of day. Now, you might say that might not change a lot, like especially for the equator. It hardly changes at all for the equator. But it does change a bit, despite what you might think. And that's only because the sun moves north and south. But so why would you need to know that? Well, specifically for places like this right here, you can see right now that the day length is short, like really short. This was basically 12 hours. This, I don't know how long that is. It's not a long time. But if you were to, oh, that's what went wrong. If you were to go halfway into the year, the length of day is significantly longer. In fact, at a very specific point, there is a point. This point, it's basically never nighttime at that point. And above it, it is also never night. Where at the pole, it's like this for half the year. But for this point, it's only for a single day. For a single day, there is no such thing as night. Fascinating. If you then change it to the other half of the year, the same thing happens, but it reversed. where at this specific point, for one day, there is no day. And this is repeated on the southern hemisphere. So day length changes dramatically depending on where you are and across the year, which is why the poles have days that are so long, half a year long, and then nights that are equally as long. They aren't exactly equal, as explained earlier, but basically. And via this, you can actually see some things that Artifexian has shown in his videos. For example, the northern sea ice and southern sea ice. Well, I can definitely see why a lot more ice would show in the southern hemisphere around this time, there being no light and all. And same thing with the north. No light, no reason for the ice to melt. Perfect reason for it to be like that. And honestly, that was the most fun during this program. Seeing things that I knew, but explained in a way better way. And this is why I think that this program should be given to everyone. Because at a glance, you can see everything that you need to know. You can see exactly where ice is built up on your planet during winter and summer. You can see exactly why the Earth's axial tilt causes the differences in lengths of day. You can even see what the lengths of days, what the length of day is in your region at a time in a certain time of year. And you can see that all at a glance. So, with all that in mind, what is this program missing? It is missing a couple things, and I might get to them in the future. First off, this analemma is wrong. It's not wrong as in like completely inaccurate, though because it's missing wobble, it is slightly inaccurate. It's wrong because this is from the sun's perspective. Basically, if you were to look at the Earth from the sun and look, because the Earth is a circle, right? From that distance, you can basically just see a circle of Earth, and it slowly sort of makes a weird motion. But if you were to draw a point on the very center of that circle and watch that point move across the Earth's surface, the point that path is the analemma that you're seeing right now. And this is not what you would see when looking at Earth. It is close, but in the northern hemisphere, this upper lobe is a lot shorter, and the southern hemisphere, this is longer, and this midpoint is nowhere near in the middle. So I want to create in the lower right a local analemma where you input coordinates for your planet, and it will tell you what the analemma looks like in that area, which is useful for people doing astronomy on your planet. And I don't know when I'll get to that. Eventually. Maybe never, honestly. So don't, expect it. Don't look every day for it. But if it happens, I'll probably do an update video, but it will not be long. The second thing that is wrong with it is I think there's something else wrong with it. I don't know. It's because, honestly, I worked on this project so much, and I find that with math and other things like that, if I work on something long enough, I sort of get into a zone where just, nothing else matters until I'm done. And when I'm done, I'll take a break for a couple days. Then when I come back to it, I hardly understand anything. I could probably familiarize myself with it, and I do understand a lot of it, but because it's so meticulously done, there are little tiny minute details that I cannot that I think I keep on overlooking, and I can't find them. So if you find an error, please tell me. What I think the error has to do is with it should be that the shape of the analemma should not change at all if the time between Perry 1 and North Solstice, basically, if you were to subtract these numbers, if that subtraction stays the same, if that number stays the same, no matter what these two values are, if those numbers stay the same, the shape of the analemma should not change. The sun will change its position, but the shape of the analemma should not change at all. And I think it does, but I have not tested it. And the reason why I think it's wrong is because I'm fairly certain that if it were correct, that the center point of this analemma should stay roughly in the center of the screen. And as you can see, it's not staying in the center of the screen. It's to the right of it. So any help would be appreciated with that. Other than that, I'm fairly certain that this is accurate. Oh, right. I should probably explain some other things about this too. So I've already explained this, which is the axial tilt relative to the sun. This I've been pointing to a lot. You probably guessed what it is, but it's just a little diagram of the planet going across the, Yeah, it's a diagram of the orbit of the planet around the sun across a year. Here is the exact year and day, depending you go above the amount of days in this. You can do that, by the way, by just deleting this value or by going here and pressing this arrow button. But this will tell you exactly what year it is and what day it is in that year. I will say that it might be slightly inaccurate, but the only reason why it's slightly inaccurate is because leap years, and they are a pain. Leap years are basically what happens when the length of a day does not match up nicely with the length of a year. And, well, you can see this is a decimal value, and this decimal value is not the officially documented amount of days in a year. It is the length from perihelion to perihelion, which is the true definition of a year, by the way. But, because our calendars aren't perfect, we measure everything exactly by days, and by mean solar days at that. You can see that it's not going to line up. And because of that, that's why we have leap years. Your planet will also have leap years, almost guaranteed, unless you somehow made these values perfect, which if you did, you're awesome. But anyway, you're going to have leap years, and so this might be slightly inaccurate for leap years. But I might fix that in the future, but for now, that's not gonna happen anytime soon. Another thing with that is local time. If you down here, if you input the coordinates, I'm also planning to put a local time where it puts the exact time. The issue with that is that I don't quite know how to format it, and the only reason I don't know how to format it is because, well, your world isn't going to be exactly 24 hours long, and because of that, I can't just put a 24-hour time. I could put the decimal amount of a day that it has been for that area, but I don't really know how to put that into a usable number. I have no idea. So basically, I'll give you that number. And this is the same with everything else along down the road. It might happen. It might not happen. I don't know. And it's not going to happen anytime soon. But with all of that out of the way, thank you for watching. This was my first video, as you can definitely tell by the quality. And I don't really know how I'm going to do these in the future, if I'll ever do them in the future. And any sort of advice, constructive criticism, no saying haha bad person blah stuff that is just not useful, guys. Just don't do it. Any constructive criticism, greatly appreciated. I know that this is a bit of a long video for modern audiences. I don't care. I really don't care. Yeah, I guess that's it. Oh, this is kind of structured the way that how I talk with my friends about stuff. I know that that isn't like professional quality or anything, but it's the way that I'm most comfortable with. If you have any suggestions on how to make that better, maybe that would help. Thank you. And bye.